So there was a couple of things on which I wanted to. There are a couple of things on which I wanted to be a little bit more precise. Going home yesterday, then I realized that that was not so precise. So, for example, think about the sign. Okay, when I say that dq over t for an irreversible cycle, it's less or equal than 0, and some of you say, oh, what does that mean? Okay. Why it should be intuitively, for you it was the opposite way, right? Because you have to think about this way. So instead of for a cycle, just consider an infinitesimal transformation. dq over t for a reversible transformation, it's equal to ds. For an irreversible transformation, the change in entropy is larger than the heat exchange. Okay? Because there is, you can have an irreversible transformation. Now we will make an explicit example. You can have an irreversible transformation in which there is no or little heat exchange, but the entropy goes up because it's a spontaneous transformation. Okay? So the correct sign is this one. Oh, integral over a cycle of this is 0 because it's a state function. Okay? So the integral over an irreversible cycle of this thing is less or equal than the integral over the cycle of this, which is.
Is that less than or, I mean, it is equal when it is reversible, right?
Yes.
But if it is irreversible, it is less than even.
For a general cycle, for a general cycle, an irreversible cycle can be irreversible, but by an infinitesimally small amount in some sense. Okay, so so this is the inequality which is true in general, and on irreversible cycles, I mean, so when you do integrals, okay, on irreversible cycles, the inequality sign is considered, and on reversible cycles, it's an integral. So let's make an example. Okay. So you have to help me with this because I just taught it this morning and while I was coming here. So you have to. In class today we'll do something else. So, but I wanted to clarify some concepts that I said yesterday. So suppose you have a gas in a piston, okay, at the volume VA. So let's make. And now suddenly, so how can we? What's an irreversible transformation that we can do? So and the piston is completely isolated from the environment. So there is a very good thermal insulator that does the job. Can you think of an irreversible transformation that we can do?
Just remove the piston fastly.
Yes. So when we say we let the gas expand in a reversible way, it means in a reversible way. It means that we have to move the piston very slowly, okay, and let the gas adjust. So now instead we do the opposite. Take the piston, just pull it up, okay, fast. Very fast, in such a way that the gas does not have time to expand. So we pull the piston up. So the gas goes up here. We put the piston up here. Okay? Very fast. And once we do that, then the gas expands. You can think of so what does it mean fast? Fast means this, so, and then I can ask, what's the relaxation time? What is the typical time scale? What is the typical velocity that I have to consider? Okay, so certainly if I do it faster than the fastest particle in the gas, right, the gas goes, the particles go at different velocities, and we will see this in the second part of the class. If I do it faster than that, then the gas will never realize that the piston moved up. Okay, but that's too fast. It's really, really too fast, because the velocities of the particles of the gas is very, very high. In practice, you have to do it faster than the speed of sound, because the speed of sound in the gas is the speed at which information transfers in the gas. So if you do it faster than the speed of sound, the gas, the part of the gas which is close to the wall cannot transfer the information to the rest of the gas. Hey, the wall, it's moved. Okay? So that's the typical time scale with which we have to do it. So, and then you see that, you know, what's the speed of sound in air? 300 meters per second, right? That's a lot. So when we say a reversible cycle, we mean that we have to move the piston in at a speed which is less than 300 meters per second. And it's, you know, that's good. So if we move the piston, I don't know, like 1,000 meters per second, which is quite fast, then the gas does not have time to relax. I mean, the transformation is certainly irreversible. Okay? So, and we go over here. Now I cannot put a line in between the 2 points, because the line is a series of equilibrium positions. And the gas was not in a series of equilibrium positions. There were waves that came in. You know, have you ever seen the gas expanding in vacuum? You have these waves and clouds that move and go up, and that's certainly not an equilibrium. At any given instant, it's not certainly an equilibrium position. So we move the piston fast, we hold it tight, and the gas expands and goes from VA to VB. Okay? What's the work done by the gas? Zero. Right? Because we pulled the piston. And then we let the gas expand. So the work done is zero. What's the heat exchanged? What did you say? What? What's the internal energy change? Because? Why is T constant? It's better if you reverse the reasoning, okay? So dq is 0, because I said the system is completely insulated. Okay, so dq is 0. dw is 0. dq minus dw is 0. So dt is 0. So let's assume the gas is a perfect gas. The internal energy change is 0. Okay? Because internal energy change is dq minus dw. So the temperature change is 0. So these 2 points lie along an isotherm. Okay? So the change in entropy we calculated it yesterday, right? So if the temperature of the point A and the temperature of the point B are the same, then the change in entropy is just n kb log of VB divided by VA, which is but dq is 0.
One is just for reversible.
Hmm?
You have to look at us such that, I mean, this is for irreversible. I mean, we can use this dq. We cannot use this thing, I mean dq.
Yeah, that's what I'm saying. That's exactly what I'm saying, the inequality here. Now you see the inequality. The entropy of the system has increased, but there was no heat exchange. Okay? So, this is just what I wanted. This is just what I wanted to stress about yesterday. So the inequality is okay, now. For example, we could do the following. We could bring down. So let me put a dashed line to say that there was an irreversible process going from VB to VA. Okay? Now I can go back from VB to VA in a reversible way, along an isotherm, for example. Okay, and therefore I have a cycle, right? And along this isotherm, so the entropy will just go back to SA. So the total ds of the entropy will be 0. But we go back along a cycle, and we have to do work on the system. Now we have to push down the piston slowly. Okay, we push down the system, the piston. The system does work. Okay, we do work on the system. And in order to keep it isotherm, we have to take out heat from the system. Okay, so now delta Q on the so delta Q, this is delta Q of AB is 0. Delta Q of BA will be less than 0. Will be equal to the work that we do which is the work that the system does is negative. Okay, it's equal to minus the work that we do on the system, because the cycle is the transformation is an isotherm. Okay, just a second. Everything has occurred at constant temperature, so temperature is a constant, and we end up with this thing here. Okay? All right? Okay. You had the question.
Can the system provide this work indefinitely?
Can the system?
The system provides the work indefinitely.
No, we. So the question is whether the system provides work. No, in this cycle we do work. We do work. Because in this first branch there is no work done by the system, and in the second branch we do work. Okay? In the first branch, do you understand why in the first branch the system does not do any work? Because you pull the piston up very fast, and the system does not have time to catch up with the piston. And the second part of the cycle, we have to compress, so we do work. The system does not do any work. The only work done is the area under this thing here. Under the second part, not the first part. Because in the first part I cannot write a curve. I said it's a non-equilibrium situation. So in the first part, PV is not equal to NKBT. And on the second part, PV is equal to NKBT.
What about if the system was doing work without receiving heat from the exterior?
But that's another cycle. That's another system. We're not doing that.
Okay, in this case, can the system be able to provide this work indefinitely?
Yeah, like your car can provide work indefinitely as far as you put gasoline in it. There is nothing wrong in taking heat from the outside or from a source and transforming it into work.
Not heat from outside. Not heat, just the system is doing work.
Okay. The system cannot generate work from nothing because there is conservation of energy. So that cannot be violated. And that's the first law of thermodynamics. Energy has to come from somewhere. The system cannot just generate work. It can take heat from the outside and transform it into work, as far as that's not the only change that occurs in the system. Okay? So you had a question?
Okay, does it mean that you can start with an irreversible process and then, because there we started with an irreversible process, but then later we moved from VB to VA as, which is, okay, I didn't understand how comes we started with an irreversible process, then ended up.
No, transformations can be either reversible or irreversible. Okay? In fact, reversible transformation, exactly reversible transformation, do not exist. They are an idealization. They are a very good approximation. Okay. Some transformations can be irreversible, like letting a gas expand without doing any work. Okay. Another irreversible transformation is you have two containers. You have a stop here, okay? You have gas filled here, you remove this, and gas expands in the other thing. This is an irreversible transformation, okay? It's not done in a controlled way. We don't take work out from the system in an expansion. So this is an irreversible transformation. In fact, the other example I had in mind was this one, but this one works better because you can go back. Just pushing. Here, you cannot go back. You have to go and push all the particles back into the container, right? Because once you open the top here, then all the gas comes out. But also here, you have, you don't do any work. The system does not do any work, does not get any heat from the outside. So the internal energy change is 0. The temperature is constant. The change in entropy between the situation in which it is all contained in one part and the situation in which it's contained in both parts is that. See? Now VB is twice VA. And the heat exchange is 0, so the inequality is verified. Only that now you cannot go back. But here there is nothing wrong in so there is really nothing wrong in going back to an original situation. It's the transformation that is reversible or irreversible, not the state. The state in which the state A and the state B are equilibrium states. There's nothing wrong in going between equilibrium state in an irreversible way. You can go with a reversible transformation or an irreversible transformation. Okay. Any other question?
Okay, if we consider an adiabatic system, means the charge in heat is equal to 0.
Mm-hmm.
And if we consider for the system is doing some work.
Yes.
That means the work is negative because the system is doing work.
The work is positive. Well, in our convention, when the system does the work is positive.
Okay, the system is receiving work.
Is?
Receiving work from
Okay.
the external.
Okay.
The work is negative or positive in this case?
Is negative.
Okay, in this case, the internal energy is negative.
The change in internal energy is
negative. Because Q, the change in Q is 0, the change in the work is negative.
no. It's positive. du is equal to dq minus dw. If dw is negative and dq is 0, du is positive. And this is our convention. You should get used to it.
Okay. If the system was doing some work,
Yes.
the change in work is positive.
dw is positive. Yeah.
And the change in internal energy is negative.
Of course, because the energy has to come from somewhere.
Yeah, let's say the system is losing energy.
Yes.
In this case, can the system work indefinitely?
No. Because at a certain point, it will, the internal energy will be 0, and you cannot go below. Okay. Any other question?
So this shows that entropy and heat exchange of delta Q and dQ are independent. So entropy is not completely dQ by dt.
So the question is whether entropy is exactly or not exactly dq over dt. Yes. It's not exactly. It is exactly dq over dt for a reversible, the integral of dq over dt, for a reversible transformation. Otherwise, it's not dq over dt. But there is an inequality. Okay? For reversible, it's equal. For irreversible, all right. So, I'm sorry if I insist on this thing, but it's very important that you understand this. And my suggestion is, I mean, even if you like, I've seen this thing like a million times. Okay, for my studies, for my career, and so on and so forth. But nonetheless, I had to think about. I have to think carefully about, an example. What does it mean? The inequality. So these are the concept of entropy is well defined once you understand it, but otherwise it's very slippery. Okay, you can easily, fall down. So you have to understand, to sit down and think about it and understand, do examples, trying to find counterexamples, and you will find no counterexamples. But in the process of doing it, you will become familiar and understand it. And there are several you know, once you understand this, it's a lot. It's very important for the rest of the theory of thermodynamics and statistical mechanics. Okay, so sorry I'm taking too much time on this, but it's, as I said, it's important. So before talking about, I want to finish on entropy, doing something which in Fermi's book is is towards the end of the book, but for us we do it now because this is a course on statistical mechanics, and the concept that I'm going to tell you now we will find it and we will actually explain it very well, I mean, to the level of current understanding in the statistical mechanics part of the class. So, so the concept is the following. So we say that, well, first of all, let me go back to R, which is the Avogadro number times KB. Okay, the Avogadro number is 6.03 times 10 to the 23. It's a pure number. And we introduce Planck's constant. Joule per second. Oh, it's funny, by the way. If you look at Fermi's book, Planck's constant is quoted at 6.5 times 10 to the minus 34. I don't think that's a typo. I think that in 1936 the value of the Planck constant was 6.5. So since then we have done a lot of experiments, and we have defined it better. So anyway, just a curiosity. So we say that the entropy is, consider a monoatomic gas, okay? For a monoatomic gas, CV is equal to 3/2 times R for a mole of a monoatomic gas. Otherwise, you have to multiply this by the number of moles. All right, if I do that, then my entropy becomes R 3/2 log T plus log V plus a constant. Right? By the way, logarithms are, the unit of measure of entropy is heat, so energy divided by temperature, right? So because it's dQ over T. So the units of measure of S are joules divided by Kelvin, which is the units of measure of R, because R is KB. A is a pure number times KB. KB is joules divided by Kelvin. What's the unit of measure of this term here in the sum? It should be dimensionless, right? But if I take the logarithm of Kelvin, I get the logarithm of Kelvin. If I take the logarithm of meter cubed, I get 3 times logarithm of meters. So the constant that I put here, it's not a dimensionless constant. Okay. if I want to make this a dimensionless constant, then I have to divide this by some arbitrary temperature scale, T0, and this by some arbitrary volume scale, V0. And then this is dimensionless, and this is dimensionless. But whenever there is a dimension in the game, it means that something interesting is happening, that there is some fundamental constants which are dimension-full, not dimensionless, which have to come into play. Okay. And in fact, I think the first one to realize that the constant of the dimension of action is joules per second, had to be present in nature was Gibbs. And you will see that in statistical mechanics, it's quite natural to introduce a constant which is the units of action. So this constant has to be dimension full. Now I will give you the expression. So from thermodynamics you cannot get this constant, because in thermodynamics the only thing you get are differences of entropies, right? So there is no information about this constant. The only information you get is about the coefficients in front of log V and log T. And in fact, in thermodynamics, you can distinguish between a monatomic gas, in which this is 3 half, and a diatomic gas, for example, in which this is 5 half. For both gases, by the way, the coefficients of log V is always 1, because this depends just on the equation of state, which is the same for an ideal gas, either monatomic or diatomic. This comes from the internal energy part, and that depends on the nature of the molecule. All right, so let me tell you what the constant is, and we will find it, as I said, in the second part of the class. The constant is the following: 2 pi m r to the 3 half e to the 5 half a to the 4th h cubed. Okay, so m is the mass of a mole of gas. R is R, E is Nepper's number, 2.718, blah, blah, blah. A, as I said, is Nepper's number, is Avogadro's number. And H is Planck's constant. Okay? Now, for the moment, don't, this is called Thakur tetro. E is Nepper's number. E is at the base of natural logarithms, 2.71. Okay. So instead of deriving this formula, let me show you that this contains information about microscopic physics, things which are occurring at microscopic level. So I can rewrite S as so let me write it down here. Actually, let me put the Let me put the 2 pi in here. Okay, 2 pi mr to the 3 half, t to the 3 half, a to the 4th, h cubed. Okay. Now, m is the mass of a mole of gas, right? So, if the mass of one particle of gas is small m, then capital M is small m times A. Was that was what was bothering you, the brackets? Okay. Okay, so so let me write this as R log of V 2 pi small m kb a squared 3 half t to the 3 half plus some constant. Okay, so this a squared to the 3 half is a cube, so this goes away with 3 of the 4 powers here. 1 of the power, I put it here, b over a. So v over a let me call it small v, is the volume per particle. Okay, so I have my big system. Particles are distributed at random. The concept of small v is the following. If I take a volume of size small v, then on average there is one particle in this volume. On average, because it's a random distribution. In fact, it will be a Poisson distribution. You know what's Poisson distribution? Distribution x is an integer number, let's say, minus the probability of having x is equal to minus lambda lambda to the x divided by x factorial, where lambda is the average of x. Okay, so if x is the number of particles in a volume, the average number of particles in a given volume is the ratio between, in a given volume, I don't know, omega is the ratio between omega and v, small v. And then let me write this as lambda t cube. So lambda t cube, so let's write it like this. 1 over lambda t cube is equal to 2 pi m kb times t to the 3, let's take this out, 1 half divided by h. it has units of length, lambda t. Okay. And it's proportional to h. So lambda t is proportional to h, to Planck's constant. Lambda t is proportional to t to the minus 1/2. Lambda t is proportional to mass to the minus 1/2. By the way, this is the only length that you can make with m temperature, so kb times temperature and Planck's constant. So if you know that there are particles of mass m that have a given energy, average energy, which is kbt, and quantum mechanics is playing some role, then the only length that can be relevant to the game is lambda t. This r times 5 is just a constant. Does not depend on the gas. You can put it like here. Or it's just a redefinition of lambda t if you want. Because I can put e to the 5 here. E to the 5 is, what is it? Slightly more than e squared. It's probably something around 10. So lambda t gets e to the 5/6, which is 1.9. Well, no, yeah, less than 2, around 2. So it's not. It's a factor, but it does not change. I mean, I would be more worried about the 2 pi's than the e to the 5/2.
What is really lambda t?
Hmm?
What the physical meaning behind this lambda t?
Yes, this is what I want to discuss actually now.
Why we keep about 2 pi there?
Well, okay, the 2 pi here is, you're right, I could just absorb it into another order 1 constant, which is e to the 5/2, doesn't matter. So really the 2 pi is not important. It gives us a scale, but lambda t is an order of magnitude. Okay, so let's do this actually, let's do this exercise. Take m as the mass of nitrogen, for example, okay, which is very common, or oxygen, whatever. Oxygen molecules, I think, they're very common in the atmosphere. And temperature as room temperature, and calculate this lambda t. You would see that this quantity, what do you expect? This lambda t to be very large or very small?
Not large, not small. It's just, I mean, since lambda t is like has a unit of dimension, length,
Uh-huh.
then I expect something in the order of like, it probably, I mean that's common, wavelengths, so, I mean I expect that thing, I'm not sure.
It's a wavelength, you're right, but which wavelength do you expect?
I mean, okay.
Do you expect like a kilometer,
No.
a meter, a nanometer?
Yeah, in the order of nanometer, yeah, I think.
Is that for thermodynamics quantities, is that big or small?
For thermodynamics, it is too small because thermodynamics is based on macroscopic, so this is
Exactly. So do the calculation, see by yourself what okay. So, but you see that when V, the volume per particle, becomes of order of lambda t cube, the entropy becomes 0. Hmm?
R raised to 5/2.
Not r raised to 5/2. R times 5/2. It's not raised.
Yeah, I mean,
It's not a power.
0. Okay.
So if you want, you can solve this equation. This equals 1, and you find that v is proportional to lambda t cubed. So instead, I don't know, maybe it's, depending on the parameters you put in, it's like nanometer or something much smaller. So, but when the entropy becomes 0, the statistical mechanics interpretation tells us that it has to stop there, right? It cannot go below that, because the entropy is the logarithm of the available states. It cannot be negative in some sense. So it means that something has to happen. And in fact, when v, the number of particles per volume, becomes of order of this length, then quantum effects become very important, and you can have several important. So based on this formula, do you expect quantum effect to be important more important when the particles become heavier or lighter? I mean, if I have a gas made of electrons, which are very light, okay, they weight a proton weighs 1800 times more than an electron.
So the lambda t goes to like 1/8, and if the mass is lighter, the lambda is big.
And the effect becomes bigger or smaller?
The effect will not be big, it's small.
The,
Small.
the effect becomes smaller.
Yeah. Okay, 1/λ. Okay, it's big, I think. Yeah, because this one goes 1/λ. Yeah.
Yes, the volume available, the critical volume, let's put it this way, available for a particle becomes larger. So if you try to put more particles in there, then. Okay, so the lighter the particles, the stronger the quantum effects are, and this is reasonable, right? In order to see quantum effects, you have to go and look for very small particles. Okay, so I leave you with this. So this formula is actually, it's been deduced from statistical mechanics, so in fact there's H in it, but it actually has macroscopic consequences, and this is what I want to show you now. So there are macroscopic quantities that depend on H. And this is the last thing we'll do today. Okay, so let's do the following experiment. I don't need this. We have 1 mole of solid, okay, and temperature and pressure are constant. Okay. And we want to see the vaporization of the solid. So what it means? I mean, piece of solid is always in equilibrium with the environment. Everything is always in equilibrium with the environment if you let it still for a while, right? So a solid can be particles can escape from the solid and go into vapor, and then go back to solid, and they reach an equilibrium in which there is a pressure and a temperature of vapor. That is equilibrium. That is at equilibrium with the solid. This is also true for liquids. So, for example, if you have some soda, I don't know, Coca-Cola, Pepsi, whatever you want, okay, and there is a carbon dioxide inside the liquid. Okay. But when it is in the bottle, there is carbon dioxide here. Okay? And the equilibrium pressure, I mean, there is a pressure at which there is equilibrium, and the number of molecules of carbon dioxide that go into the liquid is equal to the number of molecules on average that goes into the vacuum here, let's say the air. So what happens? Why, when you open the Coca-Cola bottle and you let it stay like that, then it's not sparkling anymore after a while? What's the difference between when there is a cap and there is no cap?
I mean, there is a pressure difference.
The volume, right? You keep putting in, so the volume of air is such that you keep putting in particles, and it has to reach a certain pressure. If the volume is large, you have to put in a lot of particles, and there is only a finite number of molecules here. So in fact, if you close very tightly a bottle of Coca-Cola, which is filled up to here, it's less sparkling. Because there is more volume and you have to put in more particles to reach the critical pressure. The same thing occurs with solids, although we don't. There are some examples of solids. There is this thing that people put in the closets. What they're called? They are these white tablets. Naphthalene, yes. That does the same thing. That evaporates, and you can smell it when you go in. So it goes in equilibrium with air. If you keep your closet open, then it's useless. It's like putting naphthalene in the kitchen because it goes to equilibrium with the larger volume. Okay, so this is the case here. So we have. Okay. So let's now. So we go now. We move the piston. We increase the volume, such that a mole of solid evaporates. Okay, like here, we increase the volume such that a mole of the gas which is in the Coca-Cola goes. And so we ask, and we want to link these two variables, T and P, the pressure and the temperature at which this thing goes. So in the evaporation of the solid, this occurs at constant temperature. We have the entropy of the vapor minus the entropy of the solid. It's equal to the heat absorbed by the environment because it requires some work to make the solid evaporate. And we said we keep the things at constant temperature. So it means that there is an external reservoir, an external source of heat that is giving heat to the system to let the vapor go out, divided by the temperature. Okay, so the heat necessary to make a mole of substance evaporate is called latent heat. There is a latent heat of evaporation, there is a latent heat of fusion. Whenever there is a phase change, there is a latent heat. And we will actually see the origin of this thing in statistical mechanics. And usually, just a second, usually people call this lambda, so let's call it lambda. Yes, who had the question? Somebody?
Is that the heat absorbed by the environment?
No, the heat absorbed by the system, sorry, from the environment. Heat absorbed by the system from the environment. Okay? The entropy of vapor, we know it. It's this, it has this form. The entropy of the solid, we don't know it, but let me give you an approximate form for the moment. You see why the constant is important here? Because we say we usually look at transformations between different states of the same phase. Okay, we expand the gas, we compress a gas, we look at the solid when it expands, and so on and so forth. But so the constant is the same. If you're talking about gas and gas, the constant is the same and will drop out from this difference. But if we have a phase change, the constants between different phases are different. So they do not drop out. Okay? So you see why in this quantity here there will be H, Planck's constant. Okay. So we do this better in the second part of the class, but let's just for a second. Yeah, just for a second, let me do this. So for the heat exchange for the solid, it's important to consider the constant pressure because the solid is not like a gas. We don't put walls in it. In fact, you see there are no walls around the solid. So what is constant is the pressure. You have a question? The temperature, so the question is the temperature is constant. Yes, the temperature is constant. So it's the same temperature between the vapor and the solid. The transition is occurring at constant temperature. But now I need the temperature dependence of this. I need this function. I have this function. I need this function. So yesterday we said that it went something like this, right? It has to go to 0 when temperature goes to 0, because this is the third law of thermodynamics. And it has to go to 3R. Okay, so the entropy of a solid, let's say we want it at this temperature here, T. The integral between 0 nt in dt of Cp divided by T. Now, an approximate form. Okay, let's take the temperature. Let's consider this temperature, which I said it's called dB is temperature, dB is temperature, depending on French speaking or English speaking. Above this temperature, the specific heat can be considered constant. It's not exactly constant, but it's very, very good approximation. Okay, so let me break this integral, an integral between 0 and theta, in dt Cp of t divided by t, an integral between theta and capital T. In this integral, this is a constant equal to 3r. Okay? And this is a constant independent of the temperature. So, the first part here, this will be equal to 3r log of t over theta. And this part here is independent of temperature, and it actually, I mean, it's the area of this curve. Now you take this curve, you divide it by t, and you take the area. And this is, as a good approximation, this area is equal to 4r. This is an approximation. So, now we have this equation to solve. Okay? The equation is r 3 log t plus log v. Oh, by the way, log v we can take it from the gas is at equilibrium, so we can take it from the equation of state. So did I write it? Yeah. Okay. So in the equation of state, this becomes 5r plus log p minus log p. Sorry, because p and v are plus this constant here. Let me just write it at C0. And we have minus 3r log t over theta plus 4r is equal to lambda over t. So we have an equation between p and t that we can solve. And we find that the equilibrium pressure of vapor at temperature T, when a mole of substance is evaporated, you can solve this equation. Actually, I think you should do it at home for p, and you find that there is a constant times 1 divided by square root of t times e to the minus lambda divided by rt. This is something you can measure in a lab. Okay? This quantity you can measure in a lab. You just count how many calories do I have to give to the system to let a mole of solid evaporate, and I get this. Then I measure the pressure, and I get this. So from here, in principle, you can find properties which are actually dictated by quantum mechanics. I mean, it's quantum mechanics that dictates the existence of theta, because if quantum mechanics was not there, we would not have a critical temperature after which the specific heat becomes constant, and before which it goes to 0. And then Planck's constant appears explicitly here. Okay? Do you have any question? So these sorts of, before you ask any question, these sorts of experiments is quite useful in statistical mechanics. These are Gedanken experiments, thought experiments, experiments of, that you do in your mind. Let's take this thing, let's let it evaporate, and then you have to go in a lab and measure things in order to get numbers and get verification for your hypothesis. But this sort of dependence on, for example, this sort of dependence on the pressure, equilibrium pressure, this exponential of the inverse of the temperature, this is quite universal. When you have these activated processes, you find it everywhere. You find it everywhere, and it comes from these equations here. Okay. Do you have any questions?
This constant, was it found before or after quantum mechanics?
After.
So we need quantum mechanics.
Yes. Let's put it this way. Thermodynamics by itself is consistent without quantum mechanics, but there are many macroscopic processes like this which really requires quantum mechanics. Because if you think, actually, vaporization is a microscopic process. Like, there are these microscopic particles which detach from the solid and just go out. Okay. So this process of going out from the solid, it's a quantum mechanical process. So it will be consistent. Let's put it this way: thermodynamics will be consistent as it is, maybe without quantum mechanics, but will not be a theory of the things that we see around. It's like classical mechanics. In principle, there's nothing wrong with classical mechanics. Actually, people at the end of the 1800s were very happy with classical mechanics. They thought they had found everything. But then, I mean, there is no logical inconsistency. But then, you know, the other experiments came about on electricity, magnetism, and wave propagation, light propagations, and so forth, that were inconsistent with classical mechanics, that had to be resolved with special relativity, and others with quantum mechanics. So, all right, since I should now start a new topic, which is so we'll abandon we'll not really abandon, because we'll see entropy everywhere in the rest of the class, the rest of the course. So, but I have to introduce thermodynamic potentials and cycles. So I think I'll stop here for today. and we'll start tomorrow the new topic.
So in the tutorial class, because it is starting tomorrow,
Mm-hmm.
will you solve exercises or
Hmm?
will just revise this?
No, you do some exercise. You will have time to ask questions to the teaching assistant, to Marco, and he will work out at the blackboard some examples, some exercises, and give you a few exercises to do for the next tutor.